We might not realize it, but we are living in a quantum world. Everything around us is built of tiny atoms. Those atoms are made of even smaller, subatomic particles, and these don't behave according to the rules we're used to.
When you think about atoms, let's say atoms that are just at room temperature, you can think of them just like spheres that are colliding, ping pong balls, billiard balls. Once you move into the quantum regime, that's when the physics gets really interesting.
In the world of quantum mechanics, particles are no longer bouncing balls of concentrated mass. Their matter becomes smeared out over several locations at once, and they start to act more like waves.
Waves can interfere. Two waves can add up or they can cancel out depending on how they get together. In life, often you don't really see interference effects. You may see it at the ocean when waves come in and they get stronger and weaker sometimes. But actually one thing where you can beautifully see it is in a soap bubble. Here I have a soap film. Light as a wave gets reflected on the front side and the back side. And depending on the thickness of the film, these two waves can cancel or add up.
How could you investigate the physics of this microscopic world of subatomic particles, particles such as electrons?
It turns out that it is really difficult to understand how electrons exactly behave inside a material, because they're everywhere at once and they also depend on all the other electrons and where they are, and they all talk to each other strongly. It's too complicated for a normal computer. But the idea is that we can do a quantum simulation. We can use our atoms that now behave quantum mechanically as a model for these quantum mechanical electrons.
How do you get everyday atoms to behave quantum mechanically? At Harvard University's Greiner lab, the researchers make their atoms very, very cold. But how cold exactly?
If you imagine a thermometer that reaches all the way from here, like from the Earth, all the way to the moon, and you imagine the scale, and the room temperature reading is here at the moon, then we are really close to absolute zero temperature here, only the width of a hair away from zero.
If you walk into my lab, you'll see first two enormous tables that seem like they're littered with optical components, stainless steel and glass. It looks like organized chaos. But all of these components are serving a very particular purpose. They're being used to manipulate lasers that we use to manipulate our atoms. At the beginning of our experiment, the atoms are thermal, they're hot. Because of that, they move like a billiard ball or a bowling ball, let's say. If you think about the bowling ball rolling towards you and you want to slow it down, you could start throwing ping pong balls at it. And of course you need many ping pong balls in order to actually slow it down. And in our case, laser light plays the role of this beam of ping pong balls that we're throwing at the bowling ball.
Every single mirror, every single lens that you see in this experiment is carefully aligned. We need to control the laser light in all its aspects. Controlling the frequency of the laser beam is extremely important because the laser cooling will only work if we sit at the right laser frequency.
After all this work to cool the atoms, the real experiment begins. The scientists gather the cold atoms into a chamber where they condense into a quantum object many times larger than any we encounter in nature, a visible quantum cloud. The next step is to trap the atoms into a specially designed structure made of lasers.
We want to create a landscape for them. And we can do that with laser light. And you can think of this landscape as looking very similar to an egg carton. The atoms can hop between the valleys in this egg carton. They can move around in that way. And there are many of them, and they all interact with each other on this landscape. And then we can pin them in place to take a picture of where they all are. With these pictures, we can directly see where every single atom is. That allows us to see how the atoms are interacting with each other, moving around on the landscape that we've created for them. And that gives us a glimpse of what these electrons are actually doing in these materials.
So after about a second, the cloud heats and disperses away. So we have 1 second to do experiments. On a typical day, we would run the experiment, take a measurement, and we would produce thousands of images.
Because our experiment is so complex and has been built up through generations of students, it also means that when something breaks, it's not necessarily something that you're the expert in. It may have been something that was built years ago. And we do learn a lot from it, and I think that's amazing. But sometimes that can be frustrating when you just want to see the physics at the very end.
The ideas developed here in the lab will one day find their way into new technologies. One exciting prospect is finding material that would transform the way electricity is used and transported by exploiting a property called superconductivity.
Superconductors already exist today, but you need extremely cold temperatures to make them superconducting.
If you think about your laptop and you use it for a long time, you can feel it heating up. And that's because the electricity is dissipating energy as heat. With a superconductor, that wouldn't happen. Your phone battery would probably last much longer. There are so many things that we couldn't even imagine in terms of applications and the ways that a room temperature superconductor could revolutionize our society and our world. Once we have this body of research, the next step is to hand that over to our friends next door, actually, the material scientists, so that they can find a material that fits the profile that we've outlined for them. When people think about quantum mechanics, they think about maybe spooky action at a distance or weird phenomena happening that nobody really understands. But really, that's just because we don't experience it on an everyday basis. But there are laws of quantum mechanics which are just like the laws of classical mechanics, and we're just trying to learn more about what those laws are.
What I would really like to achieve is that we can create a better understanding of this fascinating microscopic quantum world. Our quantum simulator seems to be the perfect tool for that.
Okay, just to get out of the
What
shop.
do ultra-cold physicists do for fun, I guess, with their atoms?
That's right. Other than play StarCraft.
Yeah.
You have to howl at the moon. It's that way.
And there are other stripes where it adds up.